Hello, here's the first problem from the 3 on the page of your packet, Projectile Motion Links and Practice Problems. It's the ball rolling off the table. The table's 1 meter high and going 3 meters per second horizontally. And as you can see, the question's how far will it go horizontally from the edge of the table till when it hits the ground. So as you can see here, we have a sketch. We've got the initial vertical position labeled 1 meter high, and then the final vertical position 0. The initial horizontal position and final horizontal position are labeled. The initial velocity is drawn, and that's entirely horizontal. And we've also got our sign convention. Up and to the right is positive. Now we know that horizontal and vertical motion are independent, but before we can go ahead and analyze those two parts of the motion separately, we need to make sure that we know what parts of the motion are in fact horizontal and vertical initially. So we need to look at that initial velocity vector, which we're told is 3 meters per second horizontally and to the right in our diagram. So we need to make sure we know which of those, what part of that 3 meters per second is vertical and what is horizontal. If the vector was at an angle relative to gravity and relative to the ground, we would need to break that into components using our right angle trig functions. In this case, it's pretty clear to see, though, that the entire vector is horizontal. So v sub x, or the initial velocity in the horizontal direction, is 3 meters per second. In the y direction, the initial velocity is 0. So we're going to use those as our initial velocities when we do go forward and analyze vertical motion and then horizontal motion independently. Now we're ready to analyze the vertical motion. So I'm going to go ahead and write down my knowns, just like with any accelerated motion problem. So we know we start with an initial vertical position of 1 meter, a final vertical position of 0. We know our initial vertical velocity is 0. We know our acceleration is downward, and thus negative 9.8 meters per second squared. And we also know that we are looking for time, so that is our unknown. So we'll go ahead and write that down. And now we need to look for what relationship is going to connect what we do know to what we don't know. And so that easiest route is going to be that derived Galileo's equation of accelerated motion, because we have both initial and final positions. We know that the initial vertical velocity is 0, and so we can actually reduce this to have simply 1t squared in the equation, and without even needing the quadratic formula, we can go ahead and solve that for t, given the acceleration and the initial and final position. So we'll just manipulate that equation to eventually isolate t squared and ultimately solve for t, and we will plug and chug and ultimately find that that value for time, the time of flight of that ball to fall from the height of the tabletop to the ground, is, a few punches in the calculator, 0.45 seconds. And now we're ready to move on to the analysis of the horizontal motion, knowing that that 0.45 seconds is not only the time it takes to fall 1 meter, but it's also the time that this ball will be traveling horizontally at that 3.0 meters per second. And that's the information we're going to use to figure out how far it will travel horizontally in that 0.45 seconds at that velocity of 3.0 meters per second. So here we go. So just like with the vertical motion, we'll go ahead and set up our horizontal motion. Again, we'll start with a label or a title for this part of the work, just so we're clear. Every time we go to solve a problem or go back and look at our work, we'll know what we're doing. And so our knowns are the initial horizontal position, we'll call 0. Our initial vertical velocity, 3.0 meters per second. Our acceleration horizontally is 0. And thus, our average velocity is going to be the same as our initial velocity, as would be our final velocity. Velocity is not changing in the horizontal direction because there's nothing accelerating it. And so now we get to tie in the results of our analysis in the vertical direction. The ball is going to be traveling for 0.45 seconds before it hits the ground. So that's the link, the one link that connects our vertical motion with our horizontal motion. And now we can go ahead and solve for that piece of information that we're looking for. What is the final position, or what is the change in position of the ball as it's traveling through the air from the edge of the tabletop to the floor before it hits the ground? Okay, so we'll go ahead and look for that relationship that connects what we do know to what we don't know, and that is our definition of average velocity. Average velocity is change in position over time. We're looking for that change in position, or as I've set it up here, we're looking for that final position. And we know everything else, so we'll go ahead and solve for that x sub f, that final position. We'll plug in our values. X naught is 0, average velocity 3.0 meters per second. And the time, 0.45 seconds. And we'll plug and chug, and we'll see that the final position of that ball is 1.35 meter. Okay, and so since we started at a position of 0, then that change in position, or the horizontal range, is 1.35 meter. And that was what we were looking for. So we have successfully solved this projectile motion problem by breaking that motion down into vertical and horizontal parts. The vertical part we used to find the time of flight, and then using that horizontal velocity, we found out how far it would go horizontally in that time of flight. And in this case, the ball falling from the edge of the table at 3.0 meters per second horizontally will travel 1.35 meters before hitting the ground. Okay, good luck with the rest of your practice problems. Sticking with the same format of drawing a sketch, breaking any angled vectors into components, and then analyzing the vertical and horizontal motions separately is pretty much the recipe for solving any of our projectile motion problems. The link, again, between vertical and horizontal motion is the time of flight. The time it will be moving vertically is always going to be the time it's also moving horizontally, and vice versa. Okay, best of luck. Thank you. Bye.